Today, I want to talk about asymptotic equipartition property. So the previous ones review, short review of probability theories, and then we will apply that uh, into information theory. In this note, I will talk about asymptotic equipartition property, which is very, very important uh, in this course. All right. So AEP, what we call, is very important. Very important. Okay. So what is AEP? We will let x1, x2, and so on to be IID with the distribution px. Okay. Then we will define the sample entropy Hn prime to be this. Okay, that is the definition. Okay, so we can say that this is a definition. So this is defined to be minus 1 over n times log of probability of the sequence. And since it is IID, it is identically distributed, independent. So since it is independent, the joint distribution is the same as product distribution. So log of product is sum of log of each individual ones. Okay, so for example, log of p x1 x2 is equal to log of p x1 x2 for each x1 and x2s, and since this is log of product, that is nothing but log of px plus log of px2, like that. So if we do that for n random variables, IID random variables, that is nothing but summation over all I running from 1 to n log of each individual ones. Okay, so that goes, I goes from 1 to small n. So I runs from 1 to n log of p of xi. And asymptotic equipartition property says that this sample entropy converges in probability to the true entropy, which is the Shannon entropy, where h of x is this. Okay, since it is IID, we can say that say this for x1. Okay, and here in this case, this I is actually for alphabet of x, okay, or alphabet of x1. So probably a better notation for this is summation of all x within alphabet of x1, px 더미대를. Yeah, so p x1 equal to small x. So that is what I mean by this notation right here. So that is the true entropy. and where this x1 is the alphabet of a random variable x1. So this here alphabet is a script, and here is not script. It is just italicized x, capital X. So that is the true entropy. Okay. So this sample entropy, which is nothing but sum of inverse probabilities of each individual random variable, right? So that is sample entropy. As you have seen, if we treat this as a random variable y, I, that is in this form, right? Including minus as well. So yi, sum of I goes from 1 to n, divided by number of addition. So that is the expression that we have in some SN in previous pages. Sum of n random variables. So it is a sample mean. And this one converges to expectation of y1. Okay. All right. That's the meaning of this expression. Okay. So if we have this convergence in probability, then we can say the following. As n goes to infinity, the sample set omega can be divided into two mutually exclusive sets. So the typical set and non-typical set. The sequence in the typical set, the sequences in the typical set has the sample entropy hx. Those in the non-typical set have the sample entropy not equal to hx. Okay, so sample space can be divided into two sets where there is a convergence occurs, and so such a set is called a typical set. So each and every sample in this set, there is a convergence probability. And then others outside of this typical set or complement of this typical set, we call atypical set. Set in the probability of atypical set goes to 0. Okay, probability of typical set goes to 1 as n goes to infinity. And then in this within this set, convergence occurs. Okay, so in this set, sample entropy converges to the true entropy. And from the weak law of large numbers, probability of a typical set goes to converges to 1 as n goes to infinity. Okay, so what we mean by this, using the definition that we had, for each epsilon greater than 0, this means this probability of all x's, the sample mean difference with between the two goes to 1. So that is a smaller than or equal to epsilon. This probability, the probability of such a set goes to 1 as n goes to infinity. That's the note. That's the meaning of this statement. Or we can say the same thing with the atypical set. The difference between the two deviates. I mean, the deviation of the two greater than epsilon goes to 0 as n goes to infinity. So we can say the same thing in this manner, in both manner. First this way or second this way. And then I'm going to give you another way in the page that follows. Okay, that is the law of large number results. So this is weak law of large numbers because we are talking about law of large numbers in the sense of convergence in probability. Okay. Now move on to the next page. All right, so here is the next page. What do I want to say? So AEP, the asymptotic equipartition property, means this. AEP. If the sequence random variable IID with px, then this sample entropy defined to be this one, and because it is IID, it is this one. That one converges to, so this is the sample mean of this one, right? Converges to the expectation of one of them in probability due to weak law of large numbers. This means that actually this is what I have written in previous page. So probability of all sequences of x with which you can calculate the sample entropy, and then this is the absolute value of the sample entropy with the true entropy hx, and the difference is greater than epsilon, so we can say that hn prime deviates a lot from true entropy. So this is the atypical set we are talking about. In the atypical set, hn prime does not converge to h, right? Because it deviates a lot, right? But probability of atypical set goes to 0 due to weak law of large numbers. And if we take this to the other way around, let's say less than or equal to epsilon, then this probability goes to 1. And this set right here, where convergence occurs, that is called typical set, okay? So the probability of a typical set goes to 1. Probability of atypical set goes to 0 due to the definition of convergence in probability. So having said that, the following statement follows. I mean, following statement makes sense, okay? We can divide the entire sample set, omega, the set of all possible sequence of length n, into two mutually exclusive sets. Typical set, where convergence occurs. Atypical set, where convergence does not occur. So we can have these two sets divide the whole entire set of x's, okay, which is omega. Now, having said that, we can make a progress. And here, we will have a notation. So for any sequence xn, x1 through xn, that belongs to a typical set, I'm going to use this notation following the Carver and Thomas, parameterized by epsilon, because epsilon is your choice, right? Remember that this is for any epsilon greater than 0. We have to talk about this, so it is depending upon epsilon. If you choose epsilon to be very small, convergence occurs with very large n, right? So this typical set should be parameterized by epsilon and n. This set is described to be collection of all vector x or sequence x with the condition that the sample mean converges to x, okay? So that is the set of all x's where convergence occurs. So convergence here means that for fixed epsilon and n, this sample mean deviates from x only by epsilon much, okay, or smaller, okay. So that is the typical set, okay, of sequence x, okay. So for any sequence within this set, the probability of the sequence must have the following property. So within this set, for any sequence you select, this sequence must satisfy the following property. What is that? Basically, considering this condition right here, that is the condition given upon the sequence x, okay? So that sequence must satisfy this relation, right? This condition, right? Remember the set notation. Set notation says all possible x, and there is a condition. And this is the particular set epsilon n. Right? This condition is basically based on n and omega, right? N and epsilon, which is this condition right here. Okay, so that is the notation that is used here. Just the usual set notation with a condition. So it is a collection of all x, a sequence of x that satisfy this given condition, which is parameterized by epsilon and n, okay? So that condition, if I consider, is absolute value of the sample entropy and a difference of sample entropy with the true entropy, okay? So this absolute value of the difference should be smaller than or equal to epsilon. Your your parametric choice. Okay, so epsilon could be any number that you can choose, which is greater than 0. Okay, so any positive number you choose, you can find a large enough n so that this is true. Okay, and then you can collect all those x's that satisfy this condition, and then we call it typical set. Okay, and law of large number says the probability of typical set converges to 1 as you increase n. So when n is large enough, convergence occurs. Okay. In such a case, the sequence must have the following property. So sequence goes right here, and then log of probability of such a sequence must satisfy that. But if I write this in different manner, so this one here is a sample entropy, and that is true entropy. And then if I write this right here, the sample entropy deviates from the true entropy plus or minus epsilon much. Okay, plus or minus epsilon much. That is this one, right? So the sample entropy takes a value within this interval. Okay, that is the condition for typical set. Okay, so having said that, I can write this line again with different form like that. So the sample mean deviates plus epsilon much or negative epsilon much. So I should reside within this interval. This statement is taken from this picture that we have drawn. Okay, so for any sequence that belongs to typical set, right, this has to be satisfied. Okay, and then now I have a minus sign here, and I apply both sides, all sides with a minus sign. Then I have inequality goes to the other way around, right? And I multiply with n on all sides. Then I have log of probability upper bounded by minus h minus epsilon, and the lower bounded by minus n times hx plus epsilon. And on that inequality, I apply the exponent relation. So maybe I need to write this. I need to do this a little slowly. So from this, I obtain right here log of 2px1 and that is upper bounded by minus n times h x minus epsilon, lower bounded by n times h minus plus epsilon. Okay, once I have done this, I can remove this by applying two 2, oh, sorry, I forgot the minus sign here. I raise to the power of 2 on each and every side. Then I have done this, then 2 of log 2, then this goes away, then it becomes the probability of the sequence, and the probability of sequence should be upper bounded by this much and lower bounded by this much. That's what I mean. Okay. All right. Once I have done that, basically these relation holds just with a simple manipulation of inequalities. So for any sequence X within the typical set, this must hold. Okay, so the probability of a typical sequence must satisfy this. All right, so that is one thing we need to remember. So the in shorthand notation, I will use probability of sequence X. I will use this factor as X on the bar. That should be upper bounded by this, right? Lower bounded by okay. So the in terms of exponent, upper bound has a minus sign in it for the epsilon, and then plus sign is the lower bound. Okay, so every sequence in the typical set. So this is true for every any sequence X in the typical set. This is true. Okay, for any sequence in the typical set, probability of such a sequence must be upper bounded by this much and lower bounded by this much. Okay, so if we choose epsilon to be very small, we can find large enough n. So P of X is about this much. That is what I mean. Okay. So P of X in this set as n goes to infinity for any epsilon greater than 0, this happens. This occurs. Give a little bit away and take a little bit. Okay. Give away a little bit, and take in a little bit. So that is what I mean by convergence in probability. Okay, so in having said this, that probability of each sequence in the typical set is almost the same, which is close to this number right here. So once you have calculated entropy of a single random variable, and once you have a sequence length, then you can find about the probability of each sequence in the typical set, which is this number right here. So that is that explains a little bit about the asymptotic equipartition property. So asymptotically, each sequence X in the typical set has the same probability of occurrence. That means the size of the typical set, because they are all uh, uh, they all have the equal probability, the size of the typical set should be the inverse of this probability, which is 2 to the power of nhx. So that is the number of sequences. So number of sequences in the typical set A epsilon n. Because each one is equally likely, the inverse of this size of the typical set should be the probability. Remember, where you have a uniform distribution, where you have 4 elements, then each outcome occurs with probability of 1/4. This, it is the same as this one, okay? But in this case, the number of sequences in the typical set, that is the size of the typical set, is equal to 2 to the power of nh. And each sequence in the typical set, because they are equally probable, should be inverse of the size of the typical set, which is this. So in the ballpark, that is what we are getting at in asymptotic equipartition property.